Hi there, welcome back. We are doing week 11, chapter 6, part 1 tonight, and we're going to be working on thermochemistry. Okay, so what is thermochemistry? What you want to take from this is you want to notice this term thermo here. Thermo, this root, means heat. Okay, so we're going to be dealing with heat. Not necessarily temperature, though that is part of it. Heat is a form of energy. And so what we need to do is we need to take a step back and we need to take a look at energy. Okay, so this is thermochemistry, and we'll say, and energy. Okay. So based on that, let's take a look at a few things. At the beginning, I have a bunch of stuff in there about energy and position and potential energy, and I'm going to let you guys read that. Don't skip it, you'll need it, but I think that you can read over that section. Some of the big things that you're going to need to remember out of this, though, is remember how we had the law of conservation of mass back in the second chapter? Well, in this chapter, we're going to have the law of conservation of energy. And just like in chapter 2, this basically means that energy cannot be created or destroyed. All the energy in the universe is constant. It can, however, change its form. And we specifically look at energy as stored energy, potential energy, and kinetic energy, energy in motion. So we have potential energy, and that's stored energy due to composition or position. So if we're talking about like a dam, that would be energy due to position because the water is held above it. If we're talking about something like food or gasoline, then we have potential energy due to composition. And that means that the food or the gasoline has stored energy inside it, and when we break the bonds that hold it together, we will release energy. Okay, the other form of energy that we have is kinetic energy. Okay, and kinetic energy is energy in motion. So this is the energy that exists when something is moving. Okay, moving, changing, and that kind of thing with that. All right, if you take physics, you'll do way more of this stuff. But now what we want to take a look at is let's look at some other concepts and terms. One is a state function. Okay, and energy is a state function. And a state function, it basically says that it doesn't matter where we started and it doesn't really matter where we're going. All that matters is where we are. So we sometimes say that it's independent of pathway. Okay, so if it's independent of pathway, then it doesn't matter if we go from one point to another point, or if we go from the same point here and we go down and around and end up here. Okay, so basically that's what we mean by a state function, and energy is an example of a state function. So is enthalpy, which we'll be doing next week. An important thing here is that a couple of other things, heat and work, are not state functions. So we'll get to that in a little bit. But really, one of the things that is going to go along with this is the idea that our energy change always has to be accounted for. So we're always going to be thinking of energy in terms of change. And we indicate a change by this triangle here, which means delta. So you could say delta something, and that means change. An example of that is, let's say that we have delta E. That means E final minus E initial, and it's always final minus initial. Okay, but the thing is with energy is that we're not going to know E final and we're not going to know E initial. Because of this state function, we're only going to be talking about it in terms of its change, delta E. Okay, so when we're working with that, then we would say, because energy can't be created and it can't be destroyed. So that means that the change in energy of our system is equal to the negative of change in energy of our surroundings. Okay, and what that basically means is the heat gained or lost by the system is equal to the opposite. So if our system gains 5 kilojoules, then our surroundings, oh, I ran out of room there. Our surroundings lose 5 kilojoules. Okay? All right, so now let's talk a little bit about systems and surroundings. Okay, so we have a couple of terms here. We have the term system, and we have the term surroundings. Okay, so what would a system and the surroundings be? Okay, so this can cause some questions here. So what we want to do, let's think about how this is going to work. So we define that in here. The system is the part of the universe that we're focusing our attention on. The surroundings are the things that are around it. But that can be a difficult thing to think about. Okay, so let's say that we take a block of ice and we put it outside in a bucket. I don't know. I'm not very creative tonight, I guess. Okay, here, let's, here's our bucket. It's a dish, okay? And now we're gonna put some ice in it. There we go. There's my ice in my dish. Okay, now what is going to happen if we make it hot? There, that's my fire under my ice. I'm not an artist. Okay, that's my fire under my ice. Okay, now what's gonna happen is my water is going to melt. The water will melt. Okay, now the system in this case is the ice. The surroundings in this case are the dish that my ice is in, the air around my ice, the fire under my ice. Okay, so those are everything that's around the ice. Okay, well, let's look at something. Let's look at another possibility. Let's say that we are baking bread. Okay, now if I am baking bread, okay, I'm going to need flour, and I'm going to need yeast, and I'm going to need water. We'll make a real simple bread here. We need flour, yeast, water, little salt. Okay, there we go. I'm done. Don't need anything else. Flour, water, yeast, and a little bit of salt. Okay, now this is my system. Okay, so what are my surroundings? My surroundings are my bread pan, the air directly around my bread pan, so we'll say the air in the oven, okay? These are the surroundings directly around my bread. Okay, so that's kind of what we mean by system versus surroundings. Let's think about another one. Let's think about the fact that if we take hydrochloric acid, okay, and sodium hydroxide, so you should remember this from chapter 4. You'll remember that we get water and aqueous sodium chloride. That was very messy. And aqueous sodium chloride. Well, unfortunately, you guys haven't seen this in the lab, but the other thing that we make when we do this is heat. Acid-base reactions always make heat, okay? And I'm gonna come back to this in a minute, but let's say that I'm looking at this reaction specifically. The HCl and the NaOH This is my system. All right, so the hydrochloric acid, the sodium hydroxide, these are our system. What are our surroundings? Because this is the part that's actually reacting. Our surroundings are the water. See how it's aqueous? Okay, the water, the beaker, the air around it. You could even say the temperature probe, the thermometer. Here, let me change that to thermometer. I mean, because if we're recording the heat increase, right, the temperature increase, okay, the thermometer, okay, all of these are surroundings. Okay, now let's take a look at a couple of different types of reaction. One is called an endothermic reaction. An endothermic reaction requires heat, okay? Remember my example of baking bread? If you mix all those lovely bread ingredients together and you let them sit all by themselves, you will notice an interesting reaction. Okay, if you've ever made yeast bread, you'll end up sort of working out a sourdough-like thing. It'll start bubbling and growing, and your yeast will get all excited and happy, and it'll start smelling bad or good, depending on what you're trying to do. But it will not bake bread. It'll make dough, it'll make more dough, it'll make all kinds of stuff. Then eventually it'll spoil and it'll go bad, but it will not make bread unless you turn the heat on to enough that it makes bread. Okay, so that's a good example of an endothermic reaction, baking bread. Another example of, actually we'll get to that in a minute. So when we see an endothermic reaction like this, okay, so what we'll have here is, we're gonna say, this is just, we write reaction, and that just means that the reaction's going from here, from the left to the right. And over here we have energy. Okay, so here we have our, in an endothermic reaction, here we have our reactants. Okay, now we always need to give our stuff, like it has to break the bonds that we have, and then it releases heat as it creates more bonds. Okay, so over here we have our products. So in an endothermic reaction, you can see this here, where the potential energy of the products is higher than the potential energy of the reactants. So we put more in. It's like putting energy into our bank account. That means that delta E is positive. Okay. Now, the next type of reaction that we have is an exothermic reaction. In an exothermic reaction, we produce or give off heat. Okay, and the graph for an exothermic reaction would look more like this. We would have a whole bunch of reactants with a whole bunch of energy. And you've got a little activation energy, and then they give off a whole bunch of energy when they form. Now, in this case, the products actually have less energy than the reactants do, less potential energy than the reactants do, because during the reaction, they gave off some of their heat energy, okay? So this means that our delta E will have a negative sign. Okay, an example of something like this would be that hydrochloric acid plus sodium hydroxide. Another example of this is basically anything burning. Yes, you have to give it a heat source to get the burning to start, but then it'll just keep burning until it's stopped, basically. It's like having a campfire. You know, you light it and then, woo, keeps going, okay? Now, an interesting thing with these two things. So endothermic reaction requires heat. Something that requires heat means that heat is basically a reactant. So what would that look like? Well, we could say bread ingredients plus heat yields bread. Okay, and that's our heat is a reactant. Okay, now let's look over here. Sorry, I've run out of room a bit, but what happens with this is I showed you this on the other one, HCl plus NaOH is yields heat, right? Let's look at burning. Well, in burning, you have wood plus oxygen gas yields CO2 and water and heat. Okay, so in an exothermic reaction, we produce heat and it's a product. In an endothermic reaction, we require heat and it's a reactant. Okay, so that's how you can remember that. Okay, so let's take a look at a couple of, actually one kind of specific example. It's easy to think about reactions, okay, are we exothermic or endothermic? But sometimes that can be difficult for what we call phase changes. And a phase change is just something that goes from solid to liquid to gas and back and forth, okay? In a phase change, and you'll see these in Chem 2, but I think it's very useful to show them here. So we have temperature on this axis, and we have heat added, excuse me, heat added on this axis. Okay, and a phase change diagram is always going to look like this. Okay, so where are these? Well, down here we have solid, and I'll make it this color because we can imagine it as ice. And then here I'll put a liquid here, and that's a darker blue because we'll imagine that that's water, which isn't really that color, but that's okay. And up here we have our gas. Okay, so because this is heat added, anytime we're going in this direction and we're adding heat, remember adding heat is endothermic. So if we're moving in this direction, we're endothermic. Okay, if we are moving in this direction, we are exothermic. Okay, so that means that when we go from a liquid to a solid on this line, freezing is exothermic. When we go from a gas to a liquid along this line, that means that condensing is exothermic. And then in the other way around, if we go from a solid to a liquid and we're melting, that's endothermic. And if we go from a liquid to a gas, boiling or evaporation, that will be endothermic, okay? So that's a really important thing to kind of remember there so that we know which direction we're talking about. Okay. So let's take a look at a couple of other things. First of all, let's talk about heat. I want to talk about this in the right order. Okay, so the change in energy of a system, delta E, is equal to Q plus W, where Q is heat and W is work. Okay, now let's go ahead and define a couple things here. If Q is positive, then we are endothermic. And if Q is negative, we're exothermic. And remembering this will be really, really important because you are going to need to be able to assign your signs. So it might tell you, we absorb this much heat. You need to know what that means. You need to put the right sign on it, okay? Now, if we're talking about work, or W, if W is positive, okay, if W is positive, then the surroundings are doing the work on the system. And if work is negative, the system is doing the work. A lot of times, this will become what we call pressure volume work. Okay, so what does that mean? If work is positive, the surroundings are doing the work. And I want you to think of that as like sort of like compressing, you're squeezing a gas into a smaller chamber. Okay, so this might be compressing a gas. If our system is doing the work, imagine that our gas is expanding, okay? And so you could say a system doing work, one example of that would be a gas expanding. Now, sometimes they'll just tell you the surroundings do this much work, or the system does this much work. But sometimes they'll just say we compress a gas, or our gas is allowed to expand. And then again, you're going to need to put the correct sign onto work. Okay, so let's take a look at work. Okay, now you guys can read in the slides the simple forms of work, but let me go ahead and let's work through a problem very similar to kind of a challenge problem that's in there. Okay, so let's say that we are inflating a balloon, and I'm actually going to change things just a bit here. Yeah, see, they have a hot air balloon in here, and I think that sounds crazy, crazy high. So we're going to tone it down a little bit. And we're going to say that we are inflating a balloon from 55.0 liters to 105.0 liters at 1.05 atmospheres by the addition of 250 joules of heat. Okay, and what we want to know here is what is the change in energy? All right, so I'm going to teach you some things and walk you through some things all in this one problem. So what are some of the things that you're going to need in here? Okay, well, one of the things that you're going to need to use to do this problem is you're going to need to remember that delta E is equal to Q plus W. Okay, let's start with the easy part. Let's start here by the addition of 250 joules of heat. If we're adding it in, okay, that word addition, that means that Q is equal to positive 250 joules. That's the easy part. Now we need to figure out what this W is, what this work is. So how do we do that? Well, you say work is equal to negative P delta V. And this shows you your change in volume. So this means negative P for pressure, and then V final minus V initial. All right, so we have negative 1.05 atmospheres times 105 minus 55. Okay, now if we were compressing, this would be backwards. So always remember, we can even identify here that I have V initial here and V final here. And so this is a chapter where you're going to have a lot of negatives and positives, and keep those straight. Okay, so now we have 1.05, oops, 1.05 times 50. Okay, this means that my work is equal to negative 52.5 liter atmospheres. Oh dear. Okay, so now what do we do? Because these are liters. So we have liter atmospheres. You notice that? Okay, you will always get that. Now, I can't add, sorry, hang on. I started to write it in the wrong spot. There we go. I can't add joules and liter atmospheres. That doesn't make sense. I need these to agree. So at this point in a problem like this, you will have to convert the liter atmospheres to joules. And the way that we're going to do that is by saying 101.3 joules equals 1 liter atmosphere. And actually, I don't know how I ended up. There we go, 1 liter atmosphere. Okay, so now let's take a look at this. Okay, and so we have negative 52.5 liter atmospheres times 1 liter atmosphere. This has to go on the bottom, so I can cancel it, 101.3 joules. Okay, now this is important. Don't forget to keep your negative. Okay, so now here I have negative 5,318.25 joules. Okay, and now I'll finish this off and I'll say, okay, well, my delta E is equal to Q, which is positive 250 joules, plus W, which is negative 5,318.25 joules. Okay, now I can see that I can only have 1 decimal point. Remember our adding and subtracting rules here. And actually, if I look through here, I've only got 3 significant figures that I can actually have. So let's go ahead and adjust this a little bit. If I can only have 3 significant figures right here, okay, then that means that this is going to be negative 5,320 joules, okay? And that means that because, again, we're adding, this is the last significant digit that I can have. Okay, so now I'll take this 250 minus 5,320. And what I will end up with is negative 5,070 joules, or negative 5.07 kilojoules. Okay, and that's an example of how you would do this kind of a problem. Okay, one more concept and then we'll be done for this evening. Okay, and that is enthalpy. Enthalpy, so delta E is energy, right? Enthalpy is specifically heat energy, not just energy or the change in energy of our system, but specifically the change in heat energy. So enthalpy is delta H, okay? And at constant pressure, so that means that basically just allowed to exist in the atmosphere, delta H is Q. And you might think, well, when am I not at constant pressure? And I'm actually going to tell you right now, don't worry about it, because in this class, you'll never not be at constant pressure. I don't think even in Chem 2, you'll still be doing constant pressure calorimetry. Okay, so another way of looking at that is that delta H then is equal to delta E plus P delta V. Okay, but you won't actually have to use that much in this semester. Next semester in Chem 2, you're going to need all of this. There's a lot more of this enthalpy topic, as well as Gibbs free energy and entropy in the next semester. But for now, we're just looking at heat energy. Okay, so remember that I said that that heat could be a reactant or a product. So I want you to take a look at this process from the slides. And I can't see it, so bear with me for a minute. C3H8 as a gas, or propane, plus 5 moles of oxygen gas yields 3 CO2 and 4 H2O liquid. So now and then it tells us in here that our delta H value for this is negative 2,221 kilojoules. Okay, so a couple of important things. Notice this L for liquid. If the process tells you that it's a liquid, you have to work with it as a liquid, and that's going to be really, really important next week. Your enthalpy value will be different if your state is different. So this was done at a temperature that made 4 moles of gaseous water instead of 4 moles of liquid water. This delta H value would be different. Okay, now one of the ways you can deal with this is you can bring this in here. So because our delta H value is negative 2,221, that means that we produced this much heat. Okay, so a nice way to think of that is to say that means 3 moles of carbon dioxide gas plus 4 moles of liquid water plus 2,221 kilojoules. And you can work with that whole thing just like this as part of the reaction. Now you can also leave it here, and that is totally fine, but some students really see this better if they place it in here. So now let's go ahead and take a look at a problem dealing with this, and I'm going to change it just a little bit so that I'm not completely duplicating what's in the slides. So let's say that we are going to burn well, 5 grams isn't very much if you think about it, propane, right? When you have oil or propane delivered to your house, you have it delivered by the gallons. So it's coming into your house not in grams, but in kilograms. So let's say that we are going to burn 58 kilograms of propane. And we want to know how much heat energy is produced. And the answer is, well, we can do stoichiometry, which I know is your favorite. You were all excited that there was going to be stoichiometry in this chapter. Okay. So the first thing that we need to do is we need to change this 58 kilograms to grams because our molar mass is going to be in grams. Okay, so we say, okay, well, 58 kilograms, and you won't always need to do this. The one in the slides is not like this. And 1 kilogram goes to 1,000 grams. Okay, so this means 58,000 grams. Okay, and we have 3 significant figures here, which I'll worry about at the end. Okay, so now let's take a look. We'll use that to start our stoichiometry. Okay, so we have 58,000 grams of propane, C3H8. And the next thing we need, this is still just right out of chapter 3 right now, is we need a molar mass for propane. Okay, and I forgot my periodic table again. Luckily, I have carbon and hydrogen memorized. Okay, so I have 3 times 12.011 plus 8 times 1.008. Okay, so we have 44.097 grams of propane per mole propane. Okay, now the next thing would be a mole ratio, okay? And then we're actually done. So with this, the mole ratio just comes directly from what we have here. So this is 1, 5, 3, and 4. So when we do this mole ratio, what we're going to do is we're going to say, okay, well, 1 mole of propane goes with 2,221 kilojoules. So then we'll say 1 mole of our propane. And if we were looking, say, at oxygen, then it would be 5. So again, just like in chapter 3, 4, and 5, pay really close attention to those coefficients. So 1 mole of propane goes with 2,221 kilojoules. Okay, and you might say, why am I leaving off the negative there? Well, leaving off the negative because they're saying how much heat energy is produced. They're looking for a magnitude of heat produced rather than a delta H value. If they said, what's delta H, then we would totally need that negative in there, but we don't because we're looking for a magnitude instead. Okay, so now let's take a look here. We have 58,000 divided by 44.097, and we multiply that by 2,221. And I can have 3 significant figures. So because of that, I'm actually going to toggle mine into scientific notation because I have that button on my calculator, and that will just make it easier to see. And our answer is 2.92 times 10 to the 6th kilojoules of heat produced. Okay, that takes you through part 1. I'll see you in recitation.